Good day, everyone, and welcome to our webinar series. This is our 8th webinar on various technical topics. Today, we are going to talk about wind and solar integration related studies. About 3 or 4 weeks ago, we discussed wind and solar integration studies, and we also discussed offshore wind integration studies. We talked about the inverters, inverter characteristics, modeling aspects, and key points that you need to keep in mind when you do wind and solar integration studies. In those discussions, we were mostly focusing on system level impacts. When you have faults in the system, or would the wind farms or the solar farms recover successfully? Would wind farms and solar farms recover without interacting in an unstable manner with each other? Those were the topics that we discussed in the previous presentations. Today, we are going to look at a very specific item, temporary overvoltages in wind farm or solar farm collector system. Now, we have seen in US, Europe, and many other countries, the system operators and transmission owners are insisting on doing this temporary overvoltage study to make sure that the substation equipment as well as the collector equipment will not be impacted due to overvoltages when you have to trip a feeder of a wind farm or a solar farm, or you have to trip some breakers at the substation that would isolate the wind farm or a specific feeder of the wind farm. When that happens, there is a possibility, the dangerous possibility of the voltage of the isolated part of the wind farm going high for a short period of time. If you don't control that, if that violates the ratings of equipment, temporary overvoltage withstand capability, or ratings of equipment, there is a danger that you would damage equipment on the collector system. There have been many reported instances of tens of surge arresters getting damaged due to this phenomena on collector system feeders. Now, if this is an offshore wind farm, right, you don't want this to happen, because if the cables gets damaged, that would have serious consequences. So this is a very specific study. There are very specific details that you have to keep in mind when you perform these studies and develop models in an EMT type program like PSCAD. So today we will discuss, we will have a general background discussion, which I think we already did. We also discuss what this TOV or temporary overvoltage concern is about. So today we will then discuss the modeling aspects. How do you model the transmission system, the substation? How do you model the wind or the solar farm collector system? Do we have to model the collector system in detail, like every cable segment, every wind turbine or the solar inverter? Do we have to model all of them? Or can we aggregate the collector system and some of the wind turbines for this study? For our system level studies, we always aggregated the wind farm. Today, we will talk about a method that we can use to aggregate the collector system electric network. If the collector system is made up of cables, cable segments, how do we aggregate it into a single cable, equivalent cable? So we will discuss that. Then I will show you some typical results, and then, as we always do, demonstrate or open up some PSCAD simulation examples. Just to get everyone on the same page, let us look at some typical wind farm layouts. At the top, you have the transmission system, in this case 132 kV. It can be anything, 230 kV, whatever. So on the high voltage bus, you can have reactors, capacitors, and in most cases, harmonic filters. In some cases, you may also have SVCs and STATCOMs to help the wind farm meet performance criteria. Then obviously you will have the station transformers, sometimes one, sometimes two or more, typically the wind farms, the collector network is at a medium voltage, typically 33 kV or thereabouts. And then you have the collector, the wind turbines themselves, right? Here I have shown a schematic representation of the feeders that connect to the collector system, right? If I go to the next slide, this is what the collector network would look like. There are many, maybe tens of wind turbines or solar inverters on a single, connected to a single feeder through the collector network. So all these are either overhead line segments or cable segments. And then in this case, there are 3 feeders, and feeder 1 has 2 branches. If you remember, for system level studies, in most cases, we would aggregate all of these wind turbines and the collector network into a single aggregated wind turbine representation. For this study, where we are talking about opening a feeder breaker and looking at the voltage on the open part of the feeder, our practice at MHI now is to model at least one feeder segment in detail. So in this particular case, the first parallel branch of feeder 1, I think it has 1, 2, 3, 4, 5, 6, 7, about 9 wind turbines connected to it. We would model all of them in explicit detail, because this is a critical study, especially if you are performing this to verify the performance of an offshore wind farm. So in these cases, in order to avoid doubts, we model at least one feeder in explicit detail. So if you include 9 wind turbine models in a single PS simulation, it will be very slow. The simulation will be very slow. So for that reason, now you can use the parallel network interface facility or capability of PSCAD, where you place different wind turbines in different PSCAD modules running on different computer cores, processors. The rest of the feeders, maybe you can equivalence them and represent them as in an aggregated manner. So we will talk about how to represent a single feeder in detail, and we will also talk about the cable and wind turbine aggregation in today's discussion. Now, to take a further look at this specific problem, now in this wind farm installation or near this wind farm installation, faults can occur at different locations, and depending on where the fault is, right, you will open one or more specific breakers to clear the fault. For example, if the fault is on feeder 1, you have to open the feeder 1 breaker, which means both parallel collector networks would get isolated from the rest of the system. The wind turbines would not be connected to the rest of the system. They are just connected to the collector cables. On the other hand, if we have a fault at the high voltage bus, then maybe you will have to open both these transformer breakers. In that case, all wind turbines, all 3 feeders and the collector systems would be connected together but isolated from the system. Okay? So depending on where the fault is, you would have different configurations of isolated wind collector networks or feeders. So in the study, we have to consider all these in order to identify the worst case or to verify that your equipment, the temporary overvoltages, are not a concern, that they are within acceptable limits. Why are we concerned about this? Because what is the issue? In very simplified terms, you can explain or think of it in terms of this diagram. So you have number of wind turbines feeding current into the collector network, which was connected to the rest of the system. So you are injecting P and Q, essentially current. Once you open the feeder, and if the wind turbines still keep injecting currents, if the control systems of wind turbines doesn't identify that the feeder is now open, and if the controls doesn't act fast enough, there is a chance that these wind turbines can keep injecting currents into the cables. Okay, and these currents have nowhere to go but into the cable capacitances, right? So current getting injected into a capacitance would obviously cause the voltage of the cables or the capacitor to go up, right? So if you look at typical results, if I show you some typical results right at this point, like this is a case where you had a fault, the RMS voltage dropped, the fault was cleared, and the breaker was this breaker was opened to clear the fault, and you can see the RMS voltage as well as of course the instantaneous actual voltage shoots up for a few milliseconds. Okay, and then in this particular case, the wind turbine controls have acted in an acceptable manner, and it had just slowly ramped down the voltage to 0 because the feeder is open. So our concern is both the magnitude of this temporary overvoltage and its duration, how long it lasts and how it drops, how fast it drops. That is the concern. If this overvoltage, temporary overvoltage is too high, and if it lasts for too long compared to the equipment TOV withstand capability, your surge arresters and maybe even cables can get damaged. So let us again look at some typical these typical results. Typically, what I have seen is these TOVs can reach around 1.5 per unit, 1.3 per unit, and so on. And depending on the controls of the wind turbine or the solar inverter, they would last for a few tens to sometimes few hundred milliseconds. Now, if I look at the surge arrestor, what I have shown here is the surge arrestor's non-linear volt current characteristics. Surge arresters are present on all these feeders, but the surge arresters are generally or typically placed to protect equipment from switching or lightning type surges, very fast or fast transients. Surge arresters typically do not limit temporary overvoltages, which last for a few cycles, and the temporary overvoltages typically occur at 60 Hertz, 50 Hertz, or they may contain low order second, third type, fourth type harmonics. These are slow events compared to lightning or high frequency switching overvoltages. So if you look at the surge arrestor characteristics, typically the surge arrestor will get into the picture if there's a fast transient and if the transient overvoltage reach about 1.8, maybe 2 per unit. In these TOVs, the voltage doesn't get to that level, right? You are somewhere here, and the surge arrestor is acting in a linear manner. It doesn't conduct current, it doesn't discharge current, surge arrestor would act as an open circuit for these type of overvoltages. So surge arrestor doesn't help, but surge arrestor also cannot withstand too much temporary overvoltage. So this is a typical, what I have shown here is a typical temporary overvoltage withstand capability of a surge arrestor. Similar characteristic curves are applicable to other equipment like cables, disconnect switches, and whatnot. So what you have to make sure is that the actual TOV, due to opening of the feeder, is within this within the equipment's capability limit. So you would do a PSCAD study, look at the voltage, look at the magnitude and the decay characteristics, and kind of compare with the capability curves of equipment. That's how you set about deciding or verifying if you have an issue, TOV issue or not. Now, right here, you can say if the wind farm controls didn't come into the picture and sort of shut down the turbine or ramp down the voltage fast enough, you will have a TOV issue. If the controls acted in a manner that the TOV remained for a longer time, 1.5, right, for more than 1 second, then probably there is a concern. So TOVs due to feed isolation you have to mitigate it through proper controls in the inverter itself. If the inverter cannot do that or doesn't do that, then you have to add other mitigating options, maybe fast grounding switches. Just have a fast acting grounding switch here, where as soon as you open the breaker, the grounding switch will also get shorted to ground. So that's kind of a background. Let us look at what we have to do in terms of PSCAD modeling to get accurate and reasonable and reliable results. So in terms of PSCAD modeling, we will start with the external transmission network. Now, here we are talking about voltages on an isolated feeder. So really, the power system characteristics, like the transmission system characteristics, will have very little to do with what happens on an isolated feeder. So for that reason, we typically model 1 or 2 buses away from the substation into the transmission network, because sometimes you want to study tripping of a transmission line connected to the point of connection. So for that reason, we don't have to model an extensive, like a large extent of the transmission system. Then if you have SVCs, STATCOMs, or similar devices, sink condensers, you have to model them, because in some cases, when you have a transmission system fault and isolate the transmission line from here, maybe the STATCOMs can help mitigate the overvoltage or TOV. So depending on your layout, if you have these elements, the recommendation is to model them or represent them using the detailed models provided by the vendor. In terms of transformers, you can use the standard models in PSCAD with standard data, the ratings, voltage, MVA, transformer impedance. Personally, my experience is transformer saturation again has very little to do with most of the scenarios that you would study, but given that it is a temporary overvoltage, right, and temporary overvoltages that last for a few cycles can impact saturation, I suggest that you include saturation in the characteristics in your model. Capacitor banks, filters, they should also be modeled, represented again in a very simple manner using standard elements. They are important though, because the TOV problem is wind turbine current feeding into cable or other capacitances. So how filters and capacitor banks contribute to that overall capacitance, depending on your scenario, depending on the breakers you switch, and depending on where your filters and capacitors are. So you need to represent them. How do we represent the collector network? So like I mentioned before, MHI, our practice over the last 2 years was to model at least one feeder whenever it is possible, whenever we have information, at least one feeder in explicit detail. So we would look at the collector system single line drawings or design information and model every cable or overhead line segment and represent every wind turbine explicit. We don't do aggregation. We don't do model scaling and so on. Rest of the feeders, you may decide to do the same thing, but that probably is not necessary because most of the time the feeders are relatively similar or identical, not always, but electrically they are pretty similar. So you may decide to represent the other feeders by a single cable or an overhead line section, right? So let me call it the aggregated representation of the feeder. Then what about the wind turbines? What you do is, just like we did for system level studies, we would take a detailed model. We would take one detailed model of the wind turbine generator provided by the manufacturer, and then scale it up or aggregate the wind turbine by the number of units, number of wind turbine units on that feed. So that is the study approach. So at this point, I will break for a minute and show you, demonstrate to you how you may build or develop this feeder network in PSCAD. Typically, you will get the cable or overhead line segment lengths and RXP values in a data sheet, which you can easily translate to a PSSC or similar data format, right? Once you have the collector system data in, let us say, PSCC or similar format, then you can use the tool that we will be providing to you, the PRSIM, which we demonstrated to you about 3 or 4 weeks ago. Some of you may not have been on that presentation. So I will quickly demonstrate to you how this collector network can be developed in PSCAD using that tool, provided that you got the data for the cables, lengths, and RXP values in some Excel or similar format, which you can easily convert to PSCC format. So I will hand over the presentation to my colleague Randu, who will demonstrate how to develop this very quickly, and then we will continue with our discussion.
Thank you, Darshan. So this is the layout of the collector network that I have taken for this demonstration. This collector system is very similar to the feeder one network that Darshan showed you in the presentation previously. Let us assume that I have the data in PSSC data format, like how I showed you. I also have drawn the single line diagram of that PSSC data network. So using both these files, the network data file and the single line diagram, we can quickly get the PSCAD model of feeder 1 using the PRSIM tool. So I will first demonstrate how to convert this information into PSCAD very easily. So this is the interface of PRSIM. First, I'm going to create a new case. Let's call it feeder 1. So now the case is created. When I right click on the case that I just created, it shows you what kind of files you can load to this case. So it says there's raw data, you can import raw data files, sequence data files, dynamic data files, and location data files. In my case, I have a network data file that's in raw data format and a location file that has XY coordinates of the buses and the transmission lines that were in the PSSC single line diagram. So I'm going to import the raw data. So as I import the network data file, under the network table, you can see it lists all the buses and the information that was in the PSSC case. Let's say you didn't have a location file. So in that case, you will have to expand the buses one by one in this tool. So you go to expand bus and pick a bus. This plus sign means you can develop the network by clicking that plus sign. I'm going to increase my canvas size so that it would. So you can develop the feeders the way you want. So I'm not going to develop the entire collector system. This is just to demonstrate. Now you can export this network into PSCAD, but I will use the location file that I had and import it to this network and develop the entire collector system at once and create the PSCAD case. So I'm going to load the location file. I can expand all the buses and transmission lines. This topology is very similar to what you saw in the single line drawing of PSSA. So once you develop the network in PRC, you can export the network. These are some features that you can enable the way you prefer. So I'm gonna represent the transmission lines using 5 sections. So this case does not have any network equivalences or dynamic data or sequence data. I'm just going to exclude those ones. And you can pick your compiler also. Okay. So PRSIM creates this intermediate case that is ready to convert to PSCAD. So this is the same network that you saw earlier. So I can launch PSCAD through this software. When I click send to PSCAD, so now you can see the collector system is developed in PSCAD, and you can use this PSCAD case as your study model for the study. Darshana?
Thank you, Randu. So we just discussed how to develop this model given that you have the data, the detailed representation of a single feeder. Next, I will briefly discuss about the aggregation of rest of the feeders or the cable networks. So we generally follow the method for cable aggregation, collect aggregation. We generally follow the method presented in an IEEE publication titled Equalencing the Collector System of a Large Wind Power Plant by Muljadi and some of his co-authors. It's a very simple methodology. If you read the paper, the method that you adopt will be very clear, right? Essentially, what you're trying to do is through some simple arithmetic based on the cable data and the current and considering the current injections from different locations where the wind turbines are placed, you try to estimate an equivalent cable inductance and a resistance for a single segment representation, aggregate representation. Then also you have to estimate an equivalent capacitance. Practically speaking, you essentially add up the different capacitances of different segments, so that your aggregated representation will have the same cable or capacitor charging as the full network. Right? That's essentially what you will achieve. And then you can also go and check the harmonic impedance looking into the full network and into the aggregate network. And if you do this right, the harmonic impedance would also be very comparable over a wide frequency range. In this case, I have shown you the comparison of the harmonic impedance from around 0 Hertz to about 2 kilohertz, right? 60 Hertz or 50 Hertz is somewhere here, and so on. So the impedance is high because we are doing this comparison on an open cable, right? When you connect it to wind turbines, of course, the equivalent impedance, series impedance, will be much, much lower. This is just a mathematical way of comparing the, aggregation and the method that you used, and that your aggregated model is a reasonable representation of the actual system. So I'm not going to talk further details. Follow this and figure out the details of this equivalent section. Once you figure out the Rx and B values of the equivalent cable segment, it is to your advantage to represent that cable segment using a traveling wave type cable or transmission line representation or model in PSCAD, right? That is because if you use a traveling wave type model, then you can use that interface or that line segment to break the simulation into number of parts and run them on parallel processors, right? So now if this is your cable segment, one end of that equivalent segment would be connected to the substation, the other end would be connected to the aggregate wind turbine unit. So the wind turbine could be on a different processor, right? So when you do this, when you implement the Bergeron model, you will have to enter your RXP data that you calculated through the aggregation technique. And if you go into the cable or line constant output section, you can check what the travel time of this segment is. You can check what the travel time or the propagation delay of this equivalent cable is. In this case, it is about 80 microseconds, right? Which means, technically speaking, you can use up to 80 microseconds as your simulation time step, right? When you break the system and the wind turbines into different processors, right? If this equivalent segment, the equivalent length is very small and the travel time is, let us say, about 5 microseconds, then you can still break it, but you have to go to very small time steps like 5 microseconds for the overall simulation, which may not be very advantageous in terms of simulation speed. Then let us also talk about, now we talked about cable aggregation. So this is the aggregated cable representation. We also have to scale or aggregate the wind turbine. Each turbine may be rated at 2 megawatts or 3 megawatts or whatever. If there are 10 wind turbines on a specific feeder or 15 wind turbines on a specific feeder, then you have to scale the single unit to reflect the aggregate response of 10 or 15 wind turbines. So for that, in PSCAD, we have this model scaling component, right? Practically speaking, like conceptually speaking, all you are doing inside here is measuring the current coming out of a single turbine and multiplying that current by n-1, right? And injecting that n-1 times the measured current through a current source to this point of connection. So if you do that, the total current flowing into the network would be n times the current of a single unit. This is simply scaling. When you try to do that, you can end up with numerical issues. To avoid numerical issues, there are few, let us say, techniques or tricks that we adopt inside this case. But when we release version 5, hopefully within the next 2 months or 3 months, you don't have to use any tricks for model aggregation. We have introduced a new numerical calculation method called modified nodal analysis. With that, you can perform perfect current dependent. You can implement perfect current dependent current sources, voltage dependent voltage sources, and so on. Right. So with version 5, you will have a more robust and solid techniques for scaling. For now, you have this model and it works as well. So scaling. There, people ask me a lot of questions about scaling and all the scaling different methods that we adopt for scaling, but in reality, this is simply what we do. So I have shown a typical representation, one feeder modeled in explicit detail. I have only modeled 3. This is the PSCAD case that I'm going to demonstrate today. So to keep things simple, I just modeled 3 wind turbines on a single feeder, and on the rest of the feeders, the wind turbines are modeled as aggregated units. Next, let us look at typical results. You already saw that. You can see there's a 3-phase to ground fault, right? In this case, on one of the feeders, I believe, the feeder is tripped, and you can see the voltage, RMS, and the real voltage, of course, shoots up, but it is controlled. Example 1. Here's another example. This is again I would say an acceptable response. What has happened here is again a 3-phase fault. The fault is cleared, the voltage ramps up, the feeder is isolated. So feeder is isolated, voltage ramps up in some fashion. The controls, wind turbine controls has held the voltage to around 1 per unit, right? The controls have, the protection has not ramped down the voltage. It has waited for about, I think, from here to here about 250 or 300 milliseconds. After 300 milliseconds, the protection is set. It has decided that, okay, something is wrong, the feeder is isolated, and the protection has acted to, ramp down the voltage. So this is also maybe acceptable. But here is a case where this is from one of our early simulations 5-6 years ago or 3-4 years ago. In this case, the controls could not handle the situation. Something went wrong, and you can see unacceptable voltages. So typical results. And in the next slide, so one of the feeders are tripped. There was a fault on the substation or on the feeder. So rest of the feeders will also see the fault or the voltage dip. One of this feeder is tripped, so you have TOV. The other feeders that remain connected should recover in an acceptable manner. And in this case, in this simulation, they have. You can see power ramping back to the pre-fault value and so on. So those are some typical results. And with that, I will finish my presentation and go on to show you some PSCAD cases. The PSCAD case I will show you and make available to you would look something like this. The wind turbines and all models are generic. So you may not see in this generic model all of the features, all of the response characteristics that I discussed here. So I will also show you some very specific cases today, but I won't be able to share them with you. In the generic case, Inside the wind turbine model, you will find all the details like we have discussed before, the generators, the aerodynamic characteristics, it's a back-to-back case, so the two inverters, the DC link and the protection, the controls, and also the filters, and also the model aggregation when applicable will all be included in that model. So with that, I think I will open my PSCAD case. I will go to my generic example where I have modeled the aggregate representation of two feeders. It's a type 4 wind farm, type 4 wind turbine units. Number of, I think I have scaled each one of these units to represent 10 wind turbines. And on the feeder where I modeled cable segments and wind turbines without aggregation explicitly, I have just modeled represented 3 to keep things simple. So in this case, in this example, I have not used the parallel network interface, but rather than running this on as a single unit, single case, I can place this wind turbine, and these 3 wind turbines in separate cases running in parallel, because I see that I have cable sections. So I can change the pi section to a Bergeron model and use the traveling wave feature, the propagation delay, to break the simulation. In this case, into 1, 2, 3, 4, 5, and with the system model 6 cases. So I don't think there's any real value in running this case. I know we haven't kept our promise and uploaded most of these cases, but I think now with this presentation, we have more time to focus on cleaning up the cases. So I promise within the next week, we will place all simulation cases from this presentation and from past presentations for you to download. So with that, I think we can say that we have come to the end of our presentation and discussion on temporary overvoltages due to disconnection of collector systems, system feeders. Thank you very much, and see you again next time.